Thank you very much to the organizers for the invitation, the opportunity to speak. My talk today is going to be based primarily on this recent paper with Muldrow, Ben, Ignacio, and Irene, all of whom are here this week, so feel free to talk with any of us. I'm going to start out by very briefly reviewing some familiar swampland conjectures. I'm then going to talk about a classification of what I'll refer to as frame simplices and power polytopes, and I'll explain these words in more detail. And then I'll end with some conclusions. Okay, so first of all, we have the distance conjecture, familiar to all of us by now, I think. Oguri and Vafa say that in an infinite distance limit, in moduli space, we should have a tower of particles whose characteristic mass scale decays exponentially. So alpha here is some order 1 number in Planck units, and more recently, my collaborators and I proposed a sharp lower bound on alpha for the lightest tower in a given infinite distance limit, namely alpha is greater than or equal to 1 over the square root of d minus 2, and this is sometimes called the sharpened distance conjecture. Finally, the emergent string conjecture tells us that any infinite distance limit is either a decompactification limit or an emergent string limit, accompanied by a tower of Kaluza-Klein modes or string oscillation modes, respectively. And in known examples, there's this nice interplay with the sharpened distance conjecture, where decompactification limits strictly satisfy the sharpened distance conjecture, and emergent string limits saturate it. And part of the goal of this talk is to understand why this is true and under what situations we can prove that this will occur. So it'll be useful for our talk to think about things in a bit more of a geometric way. This approach was pioneered by these authors here. And what we're going to do is define the so-called scalar charge to mass vectors. So for any particle tower with a characteristic mass scale m, we define this scalar charge to mass vector to be the negative of the partial derivative with respect to the ith scalar field of the log of this mass scale. So here, and throughout my talk, I'm going to assume that our scalar fields are canonically normalized. And if there are n scalar fields, then this will be an n-dimensional vector. In this language, the sharpened distance conjecture translates roughly to the statement that the convex hull of these scalar charge to mass vectors should contain the ball of radius 1 over square root of d minus 2. And I'll explain why this is by means of an example. So let's take a look at type 2b string theory in 9 dimensions. So we've compactified on a circle. We'll get a tower of Kaluza-Klein modes. We'll get winding modes for the string. We'll get winding modes for the D1 brane, oscillation modes for the string in the D1 brane. You can see that the convex hull here is this triangle. It contains this ball of radius 1 over square root of d minus 2. And indeed, there are these 2 points of tangency. These correspond to the string oscillation modes, the emergent string limits, where the sharpened distance conjecture is saturated. And everywhere else, it's satisfied with room to spare. And there's a nice way to see, in a given infinite distance limit, what the largest alpha value is for any tower. And the way we're going to do this is by projecting these scalar charge to mass vectors onto the direction of interest. So let's suppose that we're taking some infinite distance limit in the dilaton radion plane. We've set the axions to vanish, and so we're going off to infinity in this direction. The lightest tower is then going to be the Kaluza-Klein modes. And the alpha coefficient, this exponential decay constant, is going to be given by the projection of this vector into this direction, which is this vector here of length alpha. And the fact that this point lies outside this ball immediately tells us that alpha is strictly greater than 1 over the square root of d minus 2. So the convex hull determines alpha, and if we do this for all of the directions in this plane, we get a plot of alpha that looks like this. And you'll see that notably, there are just these 2 points where the sharpened distance conjecture is saturated. Indeed, there are these 2 points that are emergent string limits. And so more generally, we can argue, typically at least, that if this convex hull contains this ball, then the sharpened distance conjecture will be satisfied. So clearly, these scalar charge to mass vectors in this convex hull diagram is useful for all of these different swampland conjectures. It's also useful in that it tells us something about the different duality frames of the theory. So let's break down this triangle into 5 simplices generated by pairs of neighboring vectors. So we have one here, one here, one here, one here, and then one here. And you'll note that each of these different simplices corresponds to a different duality frame. Up here, we have a perturbative type 2b description. If we cross this line, we have S duality, and we get another type 2b description. Crossing this line, we go into a T-dual type 2a phase, and if we cross this line, we're now in a regime where we should think of this theory as being M theory on a 2 torus. So each of these simplices corresponds to a different duality frame, and as a result, we call them frame simplices. So more generally, yeah. So as I'll explain in a bit, the transition between the lines corresponds to a transition of the nature of the species scale. So if we go from a place where the species scale is given by some string scale to a place where it's given by some higher dimensional Planck scale. It is a continuous transition, but well, what we're doing here is we're kind of thinking asymptotically. And so we're then just taking this to be the geodesic ray that gives us that dividing line asymptotic. Because asymptotically, it is more of a sharp transition. Yeah. Good questions. Okay. So, so more generally, we're going to define the frame simplex. In a given infinite distance limit, we define this frame simplex to be the simplex generated by the scalar charge to mass vectors of the towers that are lighter than the species scale. So the species scale gives us this distinction between heavy towers, light towers. The ones that are lighter than or at the species scale will go into this frame simplex. And the first and main point of my talk is to classify the possible shapes that this frame simplex can take in generic infinite distance limits. So how are we going to do this? Well, the classification is going to rely on some assumptions. First of all, we have the emergent string conjecture. And we're going to take this to mean that the lightest tower in any given infinite distance limit is either a KK tower or a tower of string oscillation modes. And the species scale is given either by a string scale or a higher dimensional Planck scale. We're furthermore going to make a regularity assumption. We're going to define a regular infinite distance limit to be one that satisfies the following properties. First of all, if it is a decompactification limit, then the endpoint of this limit has to be a Ricci flat decompactification manifold, except perhaps in regions of measure 0. So the decompactification manifold doesn't have to be Ricci flat, but it asymptotically has to approach a Ricci flat manifold. We also want to insist that the lightest tower in a given decompactification limit is non-degenerate. And furthermore, we're going to say that after decompactification, if we have some infinite distance limit, which leads to a decompactification, then that limit is going to lift to an infinite distance limit in the higher dimensional theory. And we want to insist that that limit, too, is also regular, that it meets these first 2 conditions. So essentially, this is a recursive statement, that we should be able to keep going up in dimension, and this limit keeps lifting to a regular limit as we go up and up and up in dimension. Now, the emergent string conjecture, as far as we know, is just true in all quantum gravity theories. In contrast, there are examples of infinite distance limits, indeed in very simple theories that we'll look at shortly, that are not regular. So this is something that is not true of every infinite distance limit, but we're going to argue that it is in fact generic. That given some quantum gravity theory, regular limits are generic and irregular ones represent a region of measure 0. Okay. I mean, yes, something like that. A density of states that doesn't have this nice, like, constant scaling of a KK tower or exponential growth of a Hagedorn density of states would be one example. Yeah. That's a good question. Yeah, that's a good question. It seems likely, but we haven't specifically looked into that question yet. Maybe we should talk more. Yes, have not looked into it yet. Sorry. Yeah. Good. So emergent string limits, where they're at the same scale, are also regular. Good. So those are fine. But yeah, so it's if there's a splitting, then we need to impose some additional conditions on the decompactification. Yeah. Okay. Good. Yeah. Yes. Yes. Right. Yeah. Mm-hmm. Yeah. 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 Yes. I mean, we're decompactifying this manifold. So we're taking. I mean, yeah. Oh, sorry. Yeah. I guess. Yeah. I guess. Sorry. Yeah. You're right. I should revise that. Asymptotically, it can approach a non-compact manifold. Like if we have, for instance, simple example, we take a circle, we take the limit where the radius goes to infinity, and that should give us this higher dimensional theory in flat space. Is it? Yeah, the circle is the easy case. That's definitely allowed here. Yeah. Right. Sorry. Yeah. Well, a sequence of Ricci flat manifolds is also something. The claim is that the limit of these manifolds is Ricci flat. So if the manifolds themselves are Ricci flat, then that's the easy case. Yeah. That's where you may run into issues with these sorts of things. Yeah. Right. You may. Okay. Good. Okay. So I'll continue, and again, we can talk more, or we'll talk with any of my collaborators afterwards. Okay. So the way we're going to do this is kind of going up in dimension of the frame simplex. So first of all, we'll start with the vertices of the frame simplex. These are given either by the scalar charge to mass vectors of fundamental string oscillation modes or Kluser-Klein modes. In the former case, the string scale is fixed uniquely in terms of the dilaton with this 1 over square root of d minus 2 coefficient. And that tells us that the length of this vertex is 1 over square root of d minus 2. For a tower of two Kluser-Klein modes, we find that the length is given by this factor right here, which depends uniquely on the number of decompactifying dimensions n. So in particular, this is a quantized set, and if we suppose that the maximal number of dimensions n plus d is finite, say 11, then there's only a finite set. There's only a finite list of the possible lengths that these vertices can take. Now, the new insight from our most recent paper is that not only the lengths, but also the angles between adjacent vertices are also quantized. Given a pair of adjacent vertices, they are going to either both be Kluser-Klein modes or one tower of Kluser-Klein modes and one tower of string oscillation modes. And we can think about the UV completion of we'll start with the first scenario. We have here KK modes associated with the decompactification of L dimensions. Here, we have KK modes associated with the decompactification of K dimensions. That means that in sum, what we have is a D plus K plus L dimensional theory that we're compactifying first on an L manifold and then on a K manifold, or vice versa. And when we do this, the radion dependence of the KK modes of the first compactification on the radion of the second compactification is uniquely determined. It's a simple calculation, it's uniquely determined. And what that's going to do is uniquely fix this angle between these two vertices to be this right here, uniquely determined by K and L. Same thing with the second case. We have string oscillation modes, we have Kluser-Klein modes, and the UV completion of this is a string theory in d plus k dimensions. So if we start with a string theory in d plus k dimensions, we compactify on a k manifold, then the radion dependence of the string oscillation modes is going to be uniquely determined, and that's going to fix this angle. So from here, we can just keep going up in dimension. We've got the vertices, we've got the angles between different vertices, and so now we can just keep going until we get all of our towers, all of the towers that are lighter than the species scale. And what we find is this result, which encapsulates the lengths and the angles, and really everything we know about the relationships between these vectors. If the two vectors are different vertices, then their dot product is just going to be 1 over d minus 2. If these two vectors represent the same vertex, then we get this additional 1 over n here, where n is the number of decompactifying dimensions. And for the case of a string oscillation vertex, we should analytically continue n to infinity. Now, simplices fall into two categories, and this refers to Dieter's question earlier. We can either have a stringy phase, which has one string vertex and the rest Kaluza-Klein vertices, or a Planckian phase, which has no string vertices and all Kaluza-Klein vertices. And these two types of phases are distinguished by the nature of the species scale in them. In the former case, we have a string scale. In the latter case, we have a higher dimensional Planck scale. And one of the first things that you can show, simply from this relationship here between any vertices of this frame simplex, is that the pericenter of the simplex always has length greater than or equal to 1 over the square root of d minus 2. The pericenter is the point on the simplex that's closest to the origin. So this point from this relationship always has length greater than or equal to this. It saturates it only in the case of a string oscillation vertex, which has length 1 over square root of d minus 2. And an immediate consequence of this is that if you're considering an infinite distance limit, where the tangent vector of the geodesic lies in the plane spanned by these frame simplices, then that immediately gives you the sharpened distance conjecture, because it tells us that we have a tower whose alpha coefficient decays with a value that's greater than or equal to this expression here. So under this additional assumption, we get the sharpened distance conjecture. We can also, from this frame simplex definition, we can also derive the tower species pattern of these authors. So suppose that we have a frame simplex. We just argued that any two vertices of it satisfy this. And let's now suppose that one of these is given by a string vertex and the other is a Kaluza-Klein vertex. Well, that means that their dot product is going to be equal to 1 over d minus 2. And furthermore, we can rewrite this for a Kaluza-Klein vertex like so, and this for the string vertex like so, where we're setting the species scale, lambda qg, equal to the string scale. This expression is precisely this tower species pattern. And we can do a similar analysis for a Planckian phase and also derive this pattern from our rules. Conversely, one can argue that under certain assumptions, one can actually go backwards. And starting with this tower species pattern, one can essentially derive these rules as well. And I'll refer you to our paper for that discussion. Okay, so this is all a little bit abstract. Let's revisit our favorite example of type 2B string theory in 9 dimensions in our favorite triangle. We see here that all of these vertices, these 5 vertices, have the correct length. We have this one here tells us that the length of this vertex corresponds to the Kaluza-Klein modes of a single decompactifying dimension, namely a circle from 9D to 10D. Same thing here, same thing here. These vertices have the correct length, 1 over square root of d minus 2 for a string oscillator vertex. And furthermore, these angles fall into the correct value, have the correct values as well. They fall into our classification scheme. Theta 1 determined uniquely by the fact that we have one decompactifying dimension here, and theta 1, 1 determined uniquely by the fact that we have one decompactifying dimension here and one decompactifying dimension here. So this is a nice example where our classification works. All of the limits are regular. Now I want to talk about a case where we have an irregular infinite distance limit, and as a result, the taxonomy rules break down. Yes? Yeah. This is just in the circle case. And so far, we've largely looked at maximal and half-maximal supergravity. things can definitely get more complicated once we have more complicated manifolds, and that's one of the main things on our to-do list next, is to look into that. Yep. But, well, first here we have an example of something that's slightly more complicated, is an example of what can happen. So SO32 heterotic string theory, compactified on a circle without any Wilson lines, is self-T-dual. So we'll have a heterotic string phase up here, another SO32 heterotic string phase down here. We'll have a type 1 phase here, type 1 phase here, and then type 1 prime phases here and here, where, again, this is the dilaton radion plane. Now, the issues here come in the infinite distance limits that are parallel to this red self-duality line. So consider an infinite distance limit that heads off to infinity in the lower left here, parallel to this red line. In that case, the location of this vertex is going to vary along this line as a function of impact parameter, that is, a function of distance from this red line. So if we go off to infinity directly on this red self-duality line, this vertex will be located right here at the location of this green arrow. And one can check that the length of this green arrow does not fall into our classification scheme. It does not have the correct length. This angle does not have the correct angle. And the reason is that this is not a regular infinite distance limit. What we have here is a decompactification not to a 10-dimensional vacuum, but rather to a 10-dimensional running solution, where the string coupling varies with position in this extra dimension. And so, as a result, the taxonomy rules do not apply in these infinite distance limits parallel to this line. However, for any other infinite distance limit in this plane, going off to infinity in any other direction, the taxonomy rules do apply. In particular, even in an infinite distance limit in this type 1 prime phase, these Kaluza-Klein modes will asymptote to either the blue point or the yellow point, as the effects of warping vanish in the limit. And this blue triangle and this yellow triangle do, in fact, satisfy our taxonomy rules. In fact, the blue one is exactly what we had for type 2b string theory, and the yellow one is exactly what we'd find for type 2a string theory. So it's only in this measure zero subset of irregular limits where we run into problems, and the rest of the limits are regular, and our taxonomy rules apply. Yeah? It does. Yeah, that's a great question. It's a good, yeah, thanks for asking that. Yes, it does. And you can see that from the fact that because this vertex slides along this line, it's always outside this ball. And so the convex hull here will always contain this ball. Sharpen distance conjecture will always be satisfied, but the taxonomy rules will not. In this example, yes. And I'd like to believe that it's always true, but we need to do more complicated examples to really know that for sure. Okay, or we really need to prove it to know it for sure. But it would help to do more examples. Okay, so we've talked now about the classification of frame simplices. And this is really a local perspective on things. We're saying, let's look at a given infinite distance limit. Let's describe the light towers in this geometric way with these simplices. What we want to do now is try to move a little bit from a local perspective to a global perspective. We want to know under what conditions can we glue these frame simplices together to form a larger polytope, a larger convex hull, what we refer to as the tower polytope. So here we're going to make two additional assumptions. First of all, we're going to assume that there exists an asymptotically flat slice of moduli space. Something that's well known from the work of Oguri and Vafa, something that Fernando Marchesano and collaborators have been studying in detail, is the fact that, in general, moduli spaces in quantum gravity have curvature. That said, typically this curvature comes from axions, from periodic directions. And so what we can often do in quantum gravity is just set the axions to vanish, and we're left with a flat slice of moduli space, at least an asymptotically flat slice, generated by dilatons and radions. Similarly, we're also going to assume that along a generic limit in this slice, the tangent space of the slice is equal to the space generated by the vectors of the frame simplex, which again, we can usually do just by ignoring axions. Okay, so we're going to make these two additional assumptions. Now we're going to try to glue together the frame simplices over the slice to form a polytope. So for the sake of simplicity today, I'll focus on the two-dimensional case. So we're going to suppose that our moduli space has a nice, flat, two-dimensional slice within it. We're going to assume that the maximal number of dimensions in quantum gravity is 11. We're going to assume that there are no strings in 11 dimensions. And from this, we're going to immediately get a finite list of possible two-dimensional Tower polytopes. And the way that we're going to get this, essentially, in this two-dimensional case, there's a very simple way to express the consistency criteria. We have all of these different frame simplices, and the point is that we need to be able to glue them together in such a way that their angles sum up to 2 pi. So we're just going to look, how many ways can we add up the angles of frame simplices to get 2 pi? In 9 dimensions, very simple, there's only one way to do it. And it's this, by now, very familiar triangle that we have in type 2b string theory. So here, infinity tells us that we have a string oscillator vertex, and this is the only way. This is the only way to put together frame simplices such that their angles add up to 2 pi. So this is nice, and it matches maximal supergravity in 9 dimensions. In 8 dimensions, we now get 2 options. Here we are gluing 6 frame simplices together. Here we're gluing 5 frame simplices together. And both of these actually show up in maximal supergravity as orthogonal slices of the full 3-dimensional Tower polytope, ignoring axions. This also takes place in 7 dimensions. In 7D, we get 2 options, both of which show up as orthogonal slices of the Tower polytope. And so you might think that there's a pattern developing here, but then you get to 6 dimensions, and all of a sudden, there's a much more complicated zoo of possibilities. In 6D, there's 11 options for the frame simplices, some of which show up in maximal supergravity, some of which do not. And so more generally, as we've seen in 7 dimensions, all of the orthogonal slices of maximal supergravity, all of the possibilities we find show up as orthogonal slices in maximal supergravity. In our paper, we have some additional results for slices of more than 2 dimensions, and one particularly interesting fact is that for the number of dimensions of the Tower polytope equal to 11 minus the number of dimensions of spacetime, the result seems to be unique and matches maximal supergravity in the dilaton-radion plane. Other examples, though, do not have known string theory realizations. We saw some examples of this in 6 dimensions, and probably the clearest and most obvious example of this is in 10 dimensions, where we have one example, type 2b string theory, where if we go off to infinity in a strong coupling limit, we have an emergent string limit, and a weak coupling limit, we also have an emergent string limit. In type 2a, we have an emergent string limit in one direction and a decompactification limit in the other direction. But there is no known 10-dimensional theory where we have a decompactification limit in both directions. What this means is that all of these Swampland conjectures that we have, the emergent string conjecture, the sharpened distance conjecture, are not strong enough to rule out all of the possibilities that we're finding. This tells us that either there are some additional corners of the landscape that have yet to be discovered, or else there are some additional Swampland criteria that must be imposed, and either of those possibilities would, of course, be very interesting. Finally, I'm probably running out of time. Oh, questions? So the in 10 dimensions, it was the example I just said, where we could have a decompactification limit in either direction. Yes. Well, in either limit, right, we would have maximal supergravity. The point is that both limits would give us 11-dimensional maximal supergravity, the same way that the strong coupling limit of type 2a gives us 11-dimensional maximal supergravity. So the point is that, yeah, we need to have that in both directions. My guess is not possible, but the point is that it doesn't follow from the Swampland conditions that we've assumed in this talk. Yeah, there's something else you need to impose. That's right, yeah. Not as far as I know, but one really should do a more thorough study before. Yeah, I can't really say anything about it in detail. But in principle, that should be possible. Okay, so the last thing I want to mention, I'm probably running out of time, is 2 more minutes. Okay, that should be just the right amount of time. So the last thing I want to mention is in the cases where we have this tower polytope, we can naturally just take the dual of this polytope. And this dual is actually a very interesting object in its own right. We refer to it as the species polytope because the vertices of this polytope are going to tell us about the different species scales that can appear in the different phases. For lack of time, I won't say more, but I'll point you to our paper for more on the species polytope. Okay, so in conclusion, we've used the emergent string conjecture plus these additional regularity assumptions to derive rules for the geometry of the convex hull generated by the scalar charge to mass vectors. We've seen that the sharpened distance conjecture, the tower species pattern, follow from the emergent string conjecture plus these additional assumptions. So they don't follow just from the emergent string conjecture, but with some additional assumptions, they do. We've used these results to classify convex hull polytopes. We found a match with maximal supergravity in many cases, but we've also found some cases that don't show up there. And our results are quite general, but not completely general. In particular, we've ignored these issues of irregular limits, where we can have these sliding vertices. And so this is one of the things we'd like to do next, is to try to understand the possibilities for how this can happen. What happens when we have an irregular limit? What are the possibilities that happen there? We'd like to extend the analysis to the interior of moduli spaces to study what happens to the frame simplex in the interior. We'd like to look at more sophisticated examples, Tim breaking up some good ideas of places to check, 4D, 5D, less supersymmetry. And finally, I think part of the point of this whole talk is that the emergent string conjecture seems to be a very powerful statement, and it would be nice to have a more rigorous proof of the statement. Thank you.